Okay, welcome to lecture here. We'll get started in just a second. Again, we're going to start lecturing on chapter 12. Those notes are available on the Canvas site if you need them. And before we get started, if you all just in the chat box, just type here. And we'll use that as roll, so you don't have to hear me call roll or anything like that. So just type here in the chat box. And again, we'll get started here in just a sec, and those notes should be able to be found there on our Canvas site in the module section. Grab something right with here. Okay, so we'll get started, and we're going to start with chapter 12, which is chemical kinetics. And again, maybe something new for a lot of you, kinetics. You don't usually cover that in something like Chem 50 or anything like that. So there should be some new information, perhaps, for you. And again, as we go through, if you have any questions, feel free to ask them. You could ask them in the chat box. Again, if you want, you can unmute your microphone and ask them that way as well. Right now, you all should be muted. A reminder again that if you do use your microphone, it will probably flash your video up if your video is on and all that kind of stuff. But you could ask either way. Otherwise, please keep yourself muted so we don't hear anything as we're kind of lecturing. All right. So let's talk a little bit about chemical kinetics and some important things. A couple of differences, two sort of big topics in chemistry. One is thermodynamics and one is kinetics. And in terms of thermodynamics, we will get into that a little bit later on this semester as well. But you've already sort of touched upon thermodynamics, probably in Chem 50, when you talked about things like enthalpy, like delta H, heat of a reaction, right? Delta H is basically negative. It's an exothermic process, right? Heat and energy is released. The delta H is positive. It's an endothermic process where heat and energy is absorbed. So the delta H, or energy, really the first law of thermodynamics is that idea of conservation of energy. So we don't create nor destroy any energy along the way. A little bit later on in a later chapter in the semester, we'll talk about some other thermodynamic sort of properties. And one important thing about thermodynamics is what it says there. Really, when we talk about those type of things later on, we talk about entropy, we'll talk about Gibbs free energy. Really what we're looking at is the idea of whether or not a reaction will take place. Is a reaction spontaneous? Is a reaction non-spontaneous? And sometimes, and as we'll talk about when we get to that chapter, sometimes people think about the idea of a reaction being spontaneous as it occurs like super fast, like you snap your fingers, it's just going to occur. And again, that doesn't really mean, that's not really what spontaneity means. It means really under those conditions, would you expect that reaction to occur? It could occur really fast. It could occur really slow. It could be sort of moderate in terms of how fast it occurs. And that's not really where thermodynamics sort of delves into it. It does delve into the idea of, again, under these conditions, would we expect this reaction to be spontaneous? Now, what does sort of delve into how fast or how slow a reaction occurs is kinetics. So what we're going to talk about in this chapter, which is kinetics, deals with really that aspect of it. It deals with the aspect of, how fast does this reaction occur? How slow does this reaction occur? And that's ultimately what sort of kinetics really does deal with, is sort of the rate of a reaction, how fast or slow something is occurring. When we do have a reaction that is happening here. So one thing when we talk about sort of kinetics and sort of reaction is basically what's known as reaction rate. And a rate really is how fast something is happening over a period of time. And in most cases in chemistry and chemical kinetics, we deal with really solutions and we deal with molarity. And that's why we have these units typically of reaction rates of molarity over seconds. And molarity, as we talked about last time, and hopefully you remember, is moles of solute over liters of solution. And basically what we look at a lot of times in chemical kinetics is basically how the concentration of a reactant, maybe even a product, is changing over a period of time. So that gives us our molarity over seconds as our units. Again, really that's usually a change in concentration over a period of time. So in general, for example, if we have this reaction here where it is A that goes to B, in a reaction such as this, we would assume that we have a couple of things happening here. First off, this reaction is a one-way arrow, right? Which means that this reaction should definitely proceed towards the products. And because it does proceed towards the products, what we should imagine is at the start of this reaction, we pretty much have all of A, right? So at the start of this reaction, we're pretty much all A and not so much B. And as this reaction proceeds to the product side, we would expect the amount of A to go down. In addition, we would also expect the amount of B to start to increase as well. And we can basically show that relationship through what's sometimes referred to as a rate expression. And a rate expression is like what we see here. And we could say that the rate of this reaction is equal to minus the change in the concentration of A over the change in time. Now, a couple of things on this. Delta is the change. So when we talk about brackets, that is concentration. And again, in most cases, what we're talking about is molarity there. So what we're looking at is the change in molarity. So like final minus initial, right? In terms of the molarity over the change in time, which again is final minus initial in terms of time. Now, because it is a reactant A, we would expect, as I just mentioned, over time that the concentration should be coming down. And that's also why the negative is here. So the negative here for our reactants is there to indicate that we are decreasing with time. Now, when we get to our product side here on B, we have the rate is equal to the change in concentration of B over the change in time. Same idea here. That's going to be your final concentration of B minus your initial concentration of B. And that's going to be divided by your final time minus your initial time. Again, here it is a product. So we would expect as time goes on that the amount of B should start to increase. And that is why we do not see a negative here. So this is positive on our product side. And the reason for the negative or not the negative here is when we calculate the rate of a reaction, it should be a positive number. So when we calculate that rate for a particular reaction, it definitely should be a positive number. And if you just think logically about, say, A in this case, the reactants, right? So since it should be decreasing with time, what that means is when you do something like the change in the concentration of A, our final number should be smaller than our initial number. So for example, if we started with 4 molar and we picked it up at 2 molar, we would take 2 minus 4, which would give us a -2 for our concentration change. That negative and the negative that is here will turn our rate into a positive number. We don't need that for the product side because the product side, the final concentration should be larger than the initial concentration. So for example, B started at 0, ended at 2. When you take 2 minus 0, you get like a +2, and that will give you a positive rate. So we do use that negative again to indicate that we are decreasing with time the concentration of our reactants. And again, with our products, we should expect it to be increasing with time. Now, in terms of units, like I said, molarity over seconds is a very common unit that is used. Again, when we deal a lot in chemistry with solutions, we're usually talking about concentrations. In addition, when we typically run experiments, we don't usually run them for days and days and days. So what that basically means is a lot of times when we look at sort of the time of the reaction, it is usually in seconds. Any questions on that there? Yeah, the lectures will be posted on Canvas once they're done. Not immediately. It takes a little time to get it up there, but it'll be up there pretty soon after they're done. So a couple of ways that we can sort of visualize this, and kinetics in general does deal with a lot of graphs. So in this chapter, you will see a lot of graphs. You'll see a lot of pictures, and you'll have a lot of sort of data information given to you in the kinetics chapter. One here, we can see sort of visually what's going on the top there. We have A, which is sort of the black circles there, going to B, which is the red circles. So as time progresses, we see a slow transition into red as we go from reactants to products, again, signaling that we are decreasing the amount of reactants, which is all those black circles, again, starting to decrease, increasing the amount of red circles there, which would indicate our products that are being made. And you can see here at the initial sort of start of the experiment, really no red circles in here. I won't write anything because it's red, but pretty much all reactants involved. And then graphically, we also see that as well in this graph. So this is time on the X and number of molecules there on the Y. And you can see at time 0, pretty much 100% are reactants and pretty much nothing going on in terms of our products. And again, in order to make products, we need to use up some of our reactants. So we start to see that decrease happening in our reactants while we start to see a increase happening there in our products happening. Again, indicated by this sort of rate expression that's happening over here. Now, in the laboratory, one way that you can sort of follow how concentration changes is when we have reactions that involve some type of color in a solution. We can follow the change in absorbance values. So absorbance values using something like Beer's law, where A is equal to BC, where B is Beer's constant. A is absorbance, and C is concentration. And we could use this sort of very sort of simple technique to really figure out how something is changing over time. And you probably have done something like this maybe in Chem 50, where you did some experiments like this. But basically, when you do something like on a Spec 20 or some type of spectrophotometry, it's basically the same sort of process that occurs. You have a light source like you see there on the bottom left, and you shine light of a specific wavelength through your sample. And it usually will measure one of two things. It can measure absorbance, or it can measure percent transmittance. And absorbance is the amount of light that gets absorbed by the sample that doesn't necessarily reach the detector, which is on the other side, as you can see in the picture. While percent transmittance is really the ratio of light that goes into how much light actually reaches the detector behind it. In most cases, and in most experiments that you do, usually you're looking at absorbance. And absorbance is related to the actual color of the solution. So what that means is it's related to how dark of a color it is. So the darker the solution, the more absorbance you will have, and the more absorbance you will have probably indicates a higher concentration of whatever was sort of the colored species in that particular reaction. The kind of colorless or not so much color, the less absorbance you're going to have and less concentration of that guy that does make the color in this particular case. So in this reaction here with the BR2, The BR2 is, you know, sort of that color there. Everybody kind of on this side is more colorless. And this also gives you sort of a visual representation of when the reaction is over, right? So you can kind of see it is kind of going all the way to the end. No more color, which would imply we have a lot more products in this case being made because it's colorless on that side versus our reactants, which is obviously kind of that orangey color that we see, or that reddish orange type color that we see. When we do this, we usually also will look for or do a curve such as this. This is a curve of different wavelength and the absorbance values for a particular solution that you may be measuring. Typically, when we want to set the spectrophotometer, we do want to set it somewhere in this range here where we have maximum absorbance. And the purpose of that is if we set our wavelength in this area here, you can see we have this entire area where when we run samples, you know, we'll be able to get absorbance values because that's really maximally where it absorbs. If you decided, well, I want to set it like way over here in terms of the wavelength, you pretty much have about that much of absorbance that's going to work. And most likely, most, if not all of your samples will be off of the scale because of that. So usually when you do something like this, and again, if you've had experience kind of doing this, you may have done it in Chem 40, maybe Chem 50 as well. They may even use Spec 20s back then. You know, you set the wavelength to a specific one. Also really important in terms of wavelength as well is the idea of when we do set that wavelength, the color that we actually see is the complementary color to what is being absorbed. So the wavelength of what we actually see is complementary color to the wavelength being absorbed. So that's why, and maybe you thought about this before, or if you've done something like this, you know, you may pick up your solution. It may look red to you, but you may actually be setting the wavelength not in the red part of the spectrum, but actually in the complementary color to red in that wavelength. And that's the reason why, because again, the color that gets absorbed, we see the complementary color to it. So that's why, you know, people oftentimes ask, like, how come I'm not setting it in the sort of red wavelength, you know, the machine? And that's because although it appears red to us, what's actually being absorbed in, again, is that complementary color to it, or the wavelength to that complementary color. So we could use something like this, like Beer's law here. Again, we could rearrange it even. And if we rearrange it, for example, we could actually solve for concentration is the absorbance divided by Beer's constant. So this is a very sort of simple way to follow what's happening in terms of the concentrations is by following the change in absorbance, because we can back relate it. And basically that's what it says on the bottom. In this particular experiment here, we could follow the change in concentration of Br2. That little symbol there is the proportional symbol to the change in the concentration or the absorbance. So that's proportional there. So basically by following the change in absorbance, we can definitely see over time, you know, how something is changing. Now, obviously this sort of technique here works really well for things that have colors, right? If your reaction involved all colorless solutions, for example, this would be useless to you because you cannot get absorbance values of things that have no color. Everything would be an absorbance value of 0, which obviously would not help you. So that's why, again, oftentimes we don't do these type of sort of experiments if their reaction doesn't have any type of color. You need color either on a reactant, you need color on a product to be able to sort of follow the difference that's happening. So if we look at this particular reaction and we get some data points like we see here on the left, we have time versus concentration, which is a very common sort of information that's achieved. We do see that with time in terms of the BR2, we do see that his concentration is starting to decrease with time. So We see it started up here, and as time goes on, it is starting to kind of decrease with time. And we can really talk about a couple of different types of rates. We obviously, in most cases, in terms of a reaction, we'll talk about what is referred to as the average rate. And the average rate in this particular case, in terms of the BR2, is again negative, the change in concentration of BR2 over the change in time. Again, here, that means that we're going to take our final minus our initial concentration of BR2 and our final minus initial of our time. Again, this would be molarity on top. That would be like seconds on the bottom, giving us our rate. As I talked about just a second ago, in this situation, because BR2 is a reactant, the final concentration should be smaller than our initial concentration, and that should give us a negative number when we subtract that. Again, that negative and negative will give us a positive value for the average rate, and again, your rate should be a positive number. Now, the average rate and instantaneous rate are a little bit different. So the instantaneous rate is for a specific period of time. So for example, let's say you were driving your car and you drove from here to, say, Arizona or something like that. And the speed limit is, say, 65 miles per hour, give or take. Some places 70, 75. But we'll say you drove on an average from here to Arizona. You maybe on an average drove 65 miles per hour because you're law-abiding citizens and all that good stuff. But there could be a point in that entire trip, right, where if you just took sort of a window of time, say around when you get to the border there, where it goes from 70 to 75, perhaps there may be an instantaneous rate of, 30 seconds, 2 minutes, 5 minutes, where maybe you're doing 85 instead of, say, 65 miles per hour. And for that sort of window of time, that's sort of your instantaneous rate, right? So for that period of time, hopefully the police officer is not behind you at that point. But for that period of time, you're traveling perhaps a little bit faster. And there could be periods of time where maybe you're traveling a little bit slower. And then when you average it all together for the whole entire trip, perhaps you traveled again 65 miles per hour. So usually when we talk about sort of rates, we're usually referring to sort of the average rates. We can, again, for a period of time, sort of figure out an instantaneous rate of how you're traveling. And that's really what these sort of triangles are here on this particular graph. And basically, if you take the slope of the tangent of those guys, you can sort of figure out the instantaneous rate. And as you can see, it's a little bit different in each of those little sort of windows. But again, if we sort of took everybody as a whole and kind of averaged the whole entire thing, we would get more of an average rate of how this reaction is sort of traveling in terms of speed. And again, if you just kind of peek in at a particular window, it may be really fast or it may be really slow, but we get this sort of average rate for the whole thing. Now, when we take a bunch of information like here, there's a couple of things that we see. And again, we do see this sort of rate or instantaneous rate sort of happening. And we do get some different numbers along the way. And again, this is sort of a snapshot of time when the rate is happening. But there is sort of a relationship that tells us a sort of constant value in terms of how fast it's happening. And that is the little k. So I'll write the k like that. Not to be confused with pretty much every other thing we'll talk about in here, giant K, no, capital K, which is equilibrium constant. So this little k is what is known as the rate constant. It is, for all intents purposes, sort of how fast a particular reaction is sort of occurring. And this is what is sometimes referred to as a rate law here. This is a rate law. And the rate constant, like it sounds, is constant value for a particular reaction. And it is pretty much going to be the same as long as you don't sort of change things like temperature or anything like that. You'll get sort of the same rate constant. So you can see in this particular reaction, it's hovering somewhere around 3.5 times 10 to the minus 3, it looks like. Reciprocal seconds is the units there, 1/seconds. And we'll talk about this a little bit later on in this chapter as well. The units that we see associated with this rate constant will tell us the type of reaction that's happening. So as we will talk about later on in this chapter, when you get units of reciprocal seconds, that usually tells you this is what is referred to as a first order type reaction. And again, we will get more into that a little bit later. We could also see a nice little relationship there in terms of the rate of the reaction and the concentration of Br2. And we do see sort of a linear relationship, and that's very important in chemistry. A lot of things that we do will involve graphs, and it will involve sort of a that y equals mx plus b, the formula for a straight line sort of relationship that occurs. Now, not all reactions, like we talked about, will necessarily have some type of color involved. So there's got to be other ways that you can figure out what's going on in terms of concentration and so forth. So in this particular reaction, when we take something like hydrogen peroxide and it sort of decomposes into water and O2, the advantage here is it is producing a gas. Yeah? And when we produce a gas, we may think about the ideal gas law, PV equals nRT, where P is our pressure, does need to be in atmospheres, right? V is our volume, needs to be in liters, N is moles, T is temperature in Kelvin, and R is our gas constant, 0.08206 liters atmosphere Kelvin mole. So we can look at this, and because we are producing a gas, we could also measure really the change in the pressure. So you may say to yourself, why would measuring the change in pressure be helpful to figure out concentration? And hopefully you remember from Chem 50, or if not, if you take PV equals nRT and you solve for N over V would equal P over RT if you do that. And if you just think about those units we just talked about, N is moles, V is volume, which is liters, that is moles per liter, that is the molarity. And you can actually figure out the molarity of a gas by really just looking at the pressure, because R is a constant, and most likely you would do this experiment at a constant temperature, which means the T would not change. So really, it makes it very simple to figure out how a gas is changing by simply just monitoring the change in pressure that's going to occur. And that'll be over a period of time. And now you have really your rate by measuring that change in pressure, which you could relate to the concentration of a gas. And that's basically what all this is here. Again, this is our change in P. So that's our P over RT, which I just solved for on the left. And again, we add that component of time to it, gives us that molarity over seconds relationship that we're looking for in terms of how this guy is doing. This works really well because in this particular reaction, if you look at it, the only thing that is a gas is the O2, which is on our product side, which means the only way we could get pressure is we have to start producing this gas, and that will give us some pressure to occur. And because of that, we can again relate it to how it is changing over a period of time. So again, this is another way where if you perhaps can't do any type of spectrophotometry and follow colors and colors changing and absorbance values, if you do have some type of gas being generated, you could take advantage of the ideal gas law and the change in pressure and really measure how the molarity is changing. Any questions on that there? Okay. And here's just sort of a graph of what we were looking at. That's okay. We'll skip that for now. Let's talk about, though, what's happening with reactions. And as you know, when we deal with reactions or equations, we also need to deal with everybody's favorite thing, which is stoichiometry. Stoichiometry, right, is that mole-to-mole relationship that occurs in a balanced equation. And we do need to deal with that as well when we're dealing with reaction rates. So if we have this reaction here, we do see a couple relationships. One relationship is the mole-to-mole relationship, which is for every 2 moles of A, we get 1 mole of B. And again, that's just the stoichiometry. A reminder, again, that is really just the coefficients that are going on there in the balanced equation. And you do have to take that into account when you're sort of trying to look at the rate of a reaction. And that's what we see down here. These are, again, 2 rate expressions. And the rate is equal to minus because A, again, is a reactant. So it's decreasing with time. 1 over 2. So the 2 is the coefficient. So 1 over 2, we take 1 over the coefficient. And really what this does, as we'll talk about here in just a second, is it takes care of all the mole-to-mole relationship part of it, the stoichiometry part of it, all sort of in one step. So you don't have to do it individually, and you'll hopefully get the right relationship. This is our normal sort of rate expression here, the change in the concentration of A over the change in time. Same thing on the B. Our B is our product, so we don't have any negative happening here because we expect it to be increasing with time. It's the change in the concentration of B over change in time. You may ask yourself, there's really nothing in front of it like we have here. And the reason for that is the coefficient here is 1. So basically when you take 1 over 1, you get 1. And much like everything in chemistry here, we don't usually include 1. So that's why there is no 1 over the coefficient, because basically 1 over the coefficient is still 1 in this case. So in general, this is a very handy sort of way that you can relate what is going on in a particular reaction, as long as you pretty much know one piece of information. As long as you know how maybe a reactant is changing with time, as long as you know how a product is changing with time, you could figure out pretty much how everybody in a particular reaction is changing. So for example, we have this generic reaction here with coefficients of A, B, C, and D. We could say that the rate is equal to minus 1 over A, which is the coefficient, and minus because A is a reactant, the change in concentration of A over the change in time, equals minus 1 over B. Again, the minus because of it is a reactant. And again, decreasing with time, 1 over B, the change in concentration of B over the change in time. Now, when we get to C and D, we're on the product side. So as we've been talking about, we would expect it to be increasing with time. And we have 1 over the coefficient for C, change in concentration of C over time, and 1 over D, change in D over time. Again, both of these guys here are positive because they should be increasing with time. What this allows you to do is they are all equal to each other. This is usually your average rate. Quick spell it, maybe. Average rate for a particular reaction. This allows you, as I mentioned, if you know the average rate, you can figure out how all the reactants are changing. If you know the products, you can figure out how the reactants are changing. If you know the reactants, you can figure out how the products are changing with time. You could use them all related to each other. You could just pull out the ones that you need and go, hey, the rate equals minus 1 over A, change in concentration of A over the change in time. You could also just break out rate is equal to 1 over C, change in the concentration of C over the change in time. And again, because you could break them out individually, they're all equal to each other, because this rate and this rate will be the same for a particular reaction. You could set them equal to each other like we do up here on these sides here. So it's a very useful way, again, here when you calculate the actual rate for the average rate for the reaction, it should be a positive number. If you're calculating the rate of a reactant, how it's changing with time, it should end up being a negative number. If you're calculating the rate of a product, how it's changing with time, it should end up being a positive number. So Again, you do want to watch some of those negatives and positives when you're doing these things, but it does give you a very sort of simple way to calculate how everybody is changing. And again, this is sometimes referred to, as you see in this question, the rate expression. So why don't you take a moment here or two and write the rate expression for this reaction, and then we'll talk about it. Okay, so let's take a look. So we're just going to write the rate expression. So we could say that the rate equals, now our CH4 is a reactant, so it's going to be negative. The coefficient here is 1, so that's 1 over 1, so you really don't need anything there. It's going to be the change in the concentration of CH4 over the change in time. That's going to equal our O2, which is also a reactant, so that's going to be negative. They do have a coefficient of 2, so that's going to be 1 over 2, which again takes care of the mole to mole relationship, really the stoichiometry that's going on. And that's going to be the change in the concentration of O2 over the change in time. Now, when we get to our product side, again, these guys should be increasing with time. So again, the coefficient here is 1. It's going to be positive. So this would just be the change in the concentration of CO2 over the change in time. And lastly here, our H2O, which is also a product, should be increasing with time, so it will be positive. Coefficient is 2, so this would be 1 over 2, change in the concentration of H2O over the change in time. Again, I put them all equal to each other, which is perfectly fine. You again can set each of these equal to the rate. And again, as long as you know something about somebody in that reaction, it will allow you to figure out how everybody else is changing with time. But it's really important to make sure you do that 1 over the coefficient. It does take care of that mole to mole relationship when we start doing some of the calculations. If you want, as well as we'll talk about maybe a little bit later on in another example, you can do just a basic stoichiometry problem first and then sort of do the rate aspect of it next. But sometimes it's a little bit easier just kind of do it all together so you don't hopefully mess up on anything. Any questions on how to write the rate expression here? So why don't we try one then? Why don't you take a couple of minutes here and actually do one that involves a calculation. For a reaction given, I minus is changing from 1 molar to 0.868 in the first 10 seconds. Calculate the average rate in the first 10 seconds and what the change in the concentration of H plus over the change in time is. So why don't you take a couple minutes here and try to see what you got, and then we'll talk about it. Okay, so let's take a look and kind of see how we're doing. So in this particular problem here, we have a reaction. They actually gave us some information about I minus, and we're looking about H plus. So that's really a good place to start. Let's write the two rate expressions for each of those. So for I minus, we see that the rate will equal minus 1 over 3, the change in the concentration of I minus over the change in time. Again, negative because I minus is a reactant. 1 over 3 takes care of our coefficient in our stoichiometry. And then we also want to relate it to H plus, which is also a reactant. So the rate would equal minus 1 over 2. Again, the minus because it's a reactant, 1 over 2 for the coefficient, and the stoichiometry, change in concentration of H plus over the change in time. So since we do have information about I minus, we might as well start with that. So we're going to use this relationship here, and that will tell us that the rate is equal to minus 1 over 3. Now, I minus concentrations, final concentration is 0.868. Minus is initial, which is 1. And we're doing 10 seconds, so final time 10, initial time 0. And if we do all that, we will get 0.868 minus 1. Again, that's going to give us a negative divided by 10 and divided by 3 gets us a positive 0.0044. The units here would be, I'll just write underneath, molarity over seconds as our rate. So here we did get a positive rate like we talked about that you should get. And again, here, that's because when we did final minus initial, we got a negative, and that negative out here, because it's a reactant, again, turns our rate into a positive number that it should be. So that would be the average rate for this particular reaction. And now that we figured out the rate, which is this number, we also know that it is this number here that relates to H plus over the change in concentration. So if we take the rate now expression for our H plus minus 1 over 2 change in concentration of H plus over the change in time. Ultimately, what we are trying to solve for, like it shows in the problem, is we are essentially trying to solve for this guy, right? The change in concentration over the change in time, which means that we need to take our 0.0044 molar seconds will equal minus 1 over 2, the change in the concentration of H plus over the change in time. Now, this is the part where most people mess up. They multiply when they should divide, divide when they should multiply. Again, we're isolating this guy, which means we need to multiply the 2 to the other side, but not just the 2 in this case, also the negative that is there. So we need to multiply negative 2 to the other side. That is going to get us for H plus minus 0.0088 molar seconds would equal the change in the concentration of H plus over the change in time. Any question on those two answers? How we got any of the numbers or where any of the numbers came from or anything like that? So again, it's important to really make sure you understand sort of the 1 over part. It takes care of the stoichiometry, but a lot of times people, like I said, they will oftentimes sort of multiply when they should divide, or divide when they should multiply, or not divide by the sort of coefficient and stuff like that. So those are very common things. We are not in this case. So as it says up there, hopefully it said it on your handout or not. We were actually looking for this here, the change in concentration of H plus over the change in time. So if you were looking for just the change in concentration at that point, you would obviously multiply it by 10, and that would give you just the concentration part. Yeah, so the second part here is from the first part, once we figured out the rate that's going on in this reaction, that's basically the average rate, um, that rate equals the rate for everybody that's there. So it equaled this rate here, and it also equaled this rate right here as well. And what that means is we do want to yeah. Yeah, I know. So we were looking for what's up here. So that's technically what we are looking for, is what was in the problem up on top. Um, because these are equal to each other, we do want to multiply the 2 to the other side, because this is, again, -1/2. So just math-wise, we need to multiply 2 to the other side. So we get that 2 that comes over here. Right? And it's not just the 2, but it is the -2 we have to multiply to the other side to clear it out. So once you figure out the overall average rate for everybody, that equals it for anybody else that would be in this reaction as well. So for example, if we're looking at, let's see what I got here. We'll go here. So if we were looking at, say, H2O on the product side, if we look at the H2O on the product side, the rate would equal 1/2 the change in the concentration of H2O over the change in time. Now, if we were doing this for the products on the example we were just doing, we would use the rate that we found for the reaction, which was 0.0044 molar seconds, would equal 1/2 the change in the concentration of H2O over the change in time. And again, if we were looking for what the change in the concentration of H2O over the change in time, basically we have to move this 2 to the other side. So we do the same thing, multiply 2 to both sides, and we would see that we would get 0.0088 molar seconds would be how water is changing with time. You may say to yourself, that looks like the same sort of answer as we got for the previous one, and it is. The difference, though, is the negative that's important here. For our H plus, it is a reactant, so it's changing by that rate over a period of time, seconds, while our water, which is a product, is actually making it, making that rate basically over a period of time. And the relationship is like stoichiometry. If you look at the relationship here, it is a 2-to-2 relationship in terms of the stoichiometry. It's basically a 1-to-1 relationship, which means as the H plus changes, the H2O in this case would change exactly the same way in this particular case. Other questions on that? Okay. So let's try another one here. Why don't you try this one? If 2.4 times 10 to the 2 grams of NOBr, molar mass from the periodic table, 109.91 grams per mole, decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. Find the average rate of production of Br2 in molarity over seconds. So see what you come up with. Okay, let's take a look and see how we're doing. So in this case, we are given some information about NOBR, and we ultimately want to find information about BR2. So again, we could use our rate expression to help us with this. So the rate would equal minus 1 over 2, change in the concentration of NOBR over the change in time. For our BR2, it would be the rate is equal to the change in the concentration of BR2 over the change in time. Again, here it is a product, so positive, coefficient is 1, so 1 over 1 is why we don't have a number here, while our NOBR is negative, should be decreasing with time, 1 over 2, which is the coefficient here. So we do have information about NOBR. We have it sort of in grams and milliliters. We could get the molarity of that. We do need to convert our grams into moles and divide by the volume here. So the first thing we'd want to do is go 2.4 times 10 to the 2 grams. They were nice enough to give us the molar mass from the periodic table. So we'll divide by 109.91 grams per mole. And if you do that, let's see here, 2.4 to the 2. And that's not right. Yeah, so it was 2.2. 2.4 to 2 divided by 109.91 gets us something like 2.1836 moles. We want really molarity, so that is 200 milliliters, which means we should take this and divide by 0.2 liters, right? As molarity needs to be moles per liter. And if we do that, 0.2 gives us something like 10.918. Take it out a little bit of distance there. Any questions on that? Hopefully you do know how to calculate the molarity. So that really is this top part here. We do need a change in time. In this case, it is in minutes. We ultimately want to get to seconds. So again, at some point, you do have to do the conversion. I'm going to convert it into seconds right now. So basically 5 times 60, right, gives you 300 seconds. So 5 minutes is 300 seconds. Again, at some point, you got to get into seconds. So might as well do it right now. That is really the bottom part here. So we really now have everything we need to solve for the rate of this reaction. So the rate would equal minus 1 over 2. Now the change in the concentration of NOBR, because it's decomposing, is this number. So that would be minus 10.918 molar divided by really our 300 seconds, 300 minus 0 if you want. Now you may ask yourself, why did I make this negative? And it's important to realize this, although it was not explicitly told to you that that number should be negative. This is the part where you should know that it should be negative because it is a reactant, which means technically speaking, this number here came from taking final minus initial. And since our final should be less than our initial, we know that this guy actually is going to be negative in terms of how it is changing. And that's important because, again, the negative here and the negative here will give us a positive rate, which is what we're looking for when we figure out the average rate. Again, should be a positive value. So you shouldn't have a negative rate for the overall rate. Should usually always be a positive value. So again, important to keep track of sort of those negatives and positives as you do this, so you don't end up with anything wrong. So if we take our 10.91 and divide it by 300, also divided by 2, gives us a rate of 0.01, and we'll go with 8. And the units here are molarity per second. Now, this is the average rate for the reaction. We do want to relate it to our BR2, which is what we're looking for. And we see that the rate for BR2 is equal to the change in concentration of BR2 over the change in time. which means we just calculated the rate a second ago, which means that that would also be the answer for how much BR2 is being made over time. And because we took care of all the negatives and positives correctly here, we end up with a positive value for how BR2 over time is changing, which also makes sense because, again, it is a product. So we would expect this concentration to be increasing. So that's why, again, we end up with that positive number. Also, why really important that if you don't keep track of all these negatives, you would end up with a negative rate, which would have said our BR2 would have been negative over here, and that would be incorrect because that would imply that it's decreasing with time, which it is not. So it's really important to sort of keep track of those things. Again, the conceptual part to sort of understand what's happening so you don't make sort of these little mistakes that could kind of build up. Question first off on any of the way we solved it or any parts of that that I could help you with. Okay, go ahead and ask. Are you asking how I got this 0.018 or the original 0.018? So I'm assuming you're talking about this right here, right? So this is 1/2, which means it's on the bottom. So you would divide. So basically here, if we just kind of expand that part of it, it's 1/2. And we basically have the negative 10.918 and divided by 300. So math-wise, technically, we would take 1 times the 10.918 and then divide by 2, right? Because this is all on the bottom, everything here. We need to divide by the 2 and divide by the 300 to equal this number here, which is the rate. And once we had that, essentially we didn't have to do anything on the bottom one because it basically equals the rate. So that's why, again, they ended up being the same answer. Other questions on that? So this is one way that you could do it. Again, this is where we're talking about taking 1 over the coefficient. And again, sometimes it's a really easier way because it does take care of sort of the stoichiometry part. Now, you could, if you wanted to, sort of did a sort of basic stoichiometry type of calculation first, and then came back and sort of did the rate part. So let me just show you sort of an alternative way you could kind of do this one here. I'm just going to pick it up with our moles of NOBR, which is the 2.1836. So just like we started the other one, we could calculate the moles of that NOBR, which was 2.1836 moles of NOBR. And at this point, you could have did just a basic stoichiometry problem, the mole-to-mole relationship if you wanted to, and you could have just did it like normal and did for every 2 moles of NOBR, there's 1 mole of BR2. And it kind of did the stoichiometry part kind of by itself if you wanted to, and you would get 1.0918 moles of BR2, which you then could have divided by 0.2 liters, which would have gave you 5.459 molar, which then you could have divided by the 300 seconds and would give you 0.018 molar seconds. So this is essentially, kind of the step-by-step, just a regular stoichiometry part. You could kind of see what we were doing before. There's the 1/2 part that we did, where we did it here. So again, kind of doing the 1 over the coefficient sort of combos the calculation for you in sort of one step. but you can see here, you can kind of do it individually if you like as well, in a more sort of stoichiometry approach, and it will come out the same way as well. So, you could do it either way, whichever way you're more comfortable doing. Sometimes, again, 1 over the coefficient is a little bit better because, let's be honest, sometimes people forget about the stoichiometry part, and this way you hopefully won't forget about it. But again, you can see, as you can see here, you could kind of do it more of a stoichiometry type of approach, and then divide by the time at the end to bring it into sort of, that rate type of way. Question on sort of an alternative way you could kind of do this. Okay, so that is the rate expression. And again, we use the rate expression to basically take care of figuring out how reactants are changing over time, how products are changing over time. We could figure out, again, the average rate as we saw. And you really just need sort of minimum information, some type of information that you could figure out either the rate or how either a reactant or product is changing with time. And you could really figure out pretty much everybody in the reaction, what's going on with them. So let's talk about rates and some things that affect rates. And in some of these things, we will go into more detail as we go through this chapter. But one thing that affects rates is the nature of the reactants, what sort of physical kind of condition they're in. So when we have small molecules, they also tend to react a lot faster. Gases do react faster than liquids, and liquids faster than solids. Again, gas molecules are flying around, so they're constantly in motion. They also have a lot of energy because they are flying around, which allows them to react a lot faster. Obviously, liquids still able to move around a little bit more than, say, solids. Solids are just kind of sitting there, not much going on, right? You kind of have to help it along usually. But solids are reactive and can react, and some are easier than others. Powdered solids are more reactive than sort of blocks. Again, you have sort of a greater surface area for reaction to take place on. Also, there are metals that are more reactive than others, and those are like, if you remember, single replacement reactions, where you have like the activity series of metals. And that means that, if you remember what that is, an activity series is really just a list of all the elements, and things that are higher on the list are more reactive than guys lower on the list. Ones lower on the list are more reactive than guys higher on the list. And, so you've probably seen that as well. Ions themselves are usually a lot more reactive, and that's why solutions are oftentimes reactive. Have pretty good rates because they're floating around in ions, which means they're free and they're good to go as they're floating around the solution. You don't have to break apart things for them to react. They're sort of ready to go. Temperature is a huge sort of factor that affects how fast or slow a reaction takes place. Typically speaking, when we increase the temperature, we do see the reaction rate increase. While if we decrease the temperature, the opposite is sort of true. It sort of will come down. And really, all about reacting is breaking bonds, making new bonds. This is all energy dependent, really. So when we increase the temperature, everybody has more energy. Since they have more energy, they're able to react usually faster than guys at lower temperature, less energy, not as active as well, right? So even gas molecules, if you lower the temperature, right, they're going to be flying around slower, which means they're not going to be as reactive perhaps as at higher temperatures where they're just bouncing around and moving really, really fast. So as you can see there, usually, if you pop the temperature up about 10 degrees Celsius, usually you'll, for most reactions, sort of see almost a doubling in terms of the rate. And there is sort of a mathematical relationship that we'll see a little bit later on in this chapter that deals with sort of the rate and temperature and things like activation energy, which we'll talk about later on as well, and how things are affected by that. Another major sort of thing that can affect the rate of reaction are catalysts. And catalysts are, as we'll talk about a little bit later on as well, they are substances that typically will speed up a reaction. They do have catalysts that will slow down a reaction, but usually most people, when they sort of speak about a catalyst, are talking about it in the sense of speeding up the reaction. And the important part about a catalyst, as we'll talk about, is that it's not really a reactant. It's not a product. It doesn't even get used up in the reaction. It's just there usually to facilitate that reaction occurring a lot faster, a lot more efficient, as it would usually occur a lot slower if it wasn't present. And as we'll talk about as well, there's different types of catalysts. There's homogeneous catalysts, which basically means everybody's in the same phase. So perhaps they're all aqueous. There's heterogeneous, which means things can be in different phases. A lot of catalysts are solids. When you look at a chemical equation, you oftentimes will see like platinum or something written on the arrow. Maybe you'll see H plus written up on top of the arrow. And a lot of times those indicate that those guys are catalysts, H plus meaning an acid as a catalyst. And again, we'll look a little bit more into this later on in this chapter as well. Another important thing is concentration. So usually the larger the concentration of reactant molecules, the faster the reaction. Again, when we talk about concentration, molarity, which is our moles of solute over liters of solution. And let's be honest, it is the solute that's swimming around in that solution that's really what's going to react, right? So when you say, hey, you have a 5 molar sodium chloride solution, it's basically 5 moles of sodium chloride in a liter of solution, but it's really those 5 moles of sodium chloride that's available to react. So if you had like 0.2 molar sodium chloride, you would only have 0.2 moles in that 1,000 milliliters or 1 liter to react. And again, it's going to take longer for those guys to sort of find each other because there's just not as much of it there. So usually the larger the concentration, the higher the rate is, or the faster the rate, because there's a higher frequency of those guys coming in contact with each other. When we talk about gases, it does depend on pressure. As you may also remember, hopefully from 50, pressure and volume are related to each other. So as the pressure increases, the volume of a gas will decrease, right? Boyle's law. And what that means is if you really increase the pressure, all your gas molecules are now in a very small volume, which means just by that process, they are all near each other, which means they most likely will come in contact with each other a lot faster than if the pressure was really low, right? If you had a low pressure, the volume would be really high, which means, you know, maybe your gas molecules are now in a much larger volume. It's going to take a little bit longer for them to fly around and come in contact with each other. And that's going to obviously affect the rate of a reaction. It would probably slow it down in that particular case. All right. So let's then talk about the rate law here. The rate law is the relationship of the rate of a reaction to its rate constant with its concentrations raised to some power. And if we look at this generic sort of equation here, A plus A goes to B, goes to C and D. This is what a rate law looks like. And let's be clear that this is different than what we've been talking about, which is, excuse me, which is the rate expression. Here, this rate law, first off, if you think about the rate expression, we dealt with reactants, we dealt with products, we dealt with everybody. If you look at this rate law, it is the rate is equal to K times A to the X, B to the Y. A and B are only reactants. So in a rate law, only reactants involved. No products. So the rate of the reaction is only going to really be dependent on your reactants as they need to come together to start the reaction happening. And K here is our rate constant. So little k again is our rate constant. Kind of tells you how fast the reaction is taking place. A is the concentration of A in molarity usually. B is the concentration of B in molarity. X is what is referred to, as you can see there, the order with respect to A. and Y is what is known as the order with respect to B. You can kind of think of the orders as sort of the proportion that's needed for this reaction to maintain a specific rate. You know, so for example, you know, if A was 1 and B was 2, you need almost like, you know, twice the amount of B there to maintain the rate that's going on than you do A. So it's sort of proportion wise, sort of what you need to help you maintain that overall reaction. X plus Y here, if you add them together, gives you the overall order of this reaction, which sort of tells you how the reaction is sort of happening. Is it, you know, first order, where a lot of times it's just sort of one reactant decomposing or something like that, or two reactants where one really isn't have an effect on the rate. Could tell you a second order where perhaps you have two reactants, each sort of reacting together in sort of a one-to-one relationship, or maybe it's second order, you have one reactant that is, you know, sort of reacting in that sort of fashion. Now, X and Y are not the coefficients in the balance equation. So you may think, well, it's just going to be the coefficients, and they are not the coefficients. X and Y are found experimentally, which means when you get a problem that you're trying to figure out the rate law, you typically will have a table, and your table will look like, some of this here. You will have perhaps you will have a table usually of, say, the concentration of A, concentration of B. You will have the rate and molarity per second. So very, very common if you're asked, hey, can you determine the rate law for a particular reaction? You'll have this sort of table, and you'll have different experiments, like experiment 1, experiment 2, experiment 3, where say A is 4 molar here, A is 4 molar here, 2 molar, and say 4 molar here. And the rate, say, is 6, and and we'll just call it 12 just to make up some numbers. And then let's see. Do 2 molar and keep do 2 molar here. And we'll just make this up here. And again, just made up numbers. So let's go with 3. All right, so this is sort of some typical sort of table looking that you'll get. And you need to use this information to basically figure out what the rate law is. And there's a couple ways you could do it. You could kind of look at it and sort of figure out, you know, what is going on with, you know, how the concentration is changing versus how the rate is changing. And most people maybe struggle doing it that way. So I find that most people usually can benefit from doing it more of a mathematical approach. And the mathematical approach would be using an equation like this, where you take rate 2 over rate 1 equals K A to the X B to the Y divided by K A to the X and B to the Y. Now, when it says rate 2 and rate 1, doesn't mean that you necessarily go to the table and you just choose entry number 1 and entry number 2. What you are looking for when you go to that table is you're looking for 2 entries in that table where one of the concentrations remain the same and the other one varies. The idea behind this is, in math, right, you don't want too many variables. So for example, in my made up one here, hopefully it'll work. If we go to experiment 1 and we go to experiment number 2, what we do see is the concentration of A has remained the same, while the concentration of B has varied. So we could put that into that example. Also, usually when you do this, if you take the one that has the higher rate and put it on top, it usually will work out better. So what I'm going to do is, up on top, I'm going to put all the information for the second entry, which means my rate would be 12 equals K, and my A would be 4 to the X, and my Y or B would be 4 to the Y. So all that information I just put in here came from right here from the table. Now I'm going to take all the information from the first entry and put it on the bottom, which means that is 6, and that is K. My A for that guy is 4 to the X, and my B for that guy is 2 to the Y. So here I'm going to do some math. When I divide 12 divided by 6, that hopefully is 2. When I take K on top and K on the bottom, although I do not know what K is at this moment, it is called the rate constant, which means although I do not know what the number is, I should know it is a constant number, which means the K on top will equal the K on the bottom, and they will cancel each other out. When I get to the next guy, which is 4 to the X and 4 to the X is the order for this particular reaction. So although I don't know what X is at this point, I do know it's going to be the same X on top as the same X on the bottom, which means these guys will also cancel, which means when I divide the last guy here, I get 2 to the Y, which tells me that Y in this case would equal 1. By the way, if you're not sure how to actually solve that, or if you don't get pretty numbers like so, you could take the natural log of both sides, and that will drop the Y down, and divide by the natural log of 2 to both sides. And you will end up with Y is equal to 1. And sometimes you may need to do that. You could also take the log of both sides if you want. You may need to do that because you may not get really pretty numbers, nice whole numbers and stuff like that. And what that would tell us is the order with respect to B would be 1. And that's the order with respect to B in this example. Then what you would do is, and we'll continue on next time, but you would go back to the table and go, okay, I kept A constant this time. I need to keep B constant this time. And to keep B constant in my made up example, we would need to use entry number 1 and entry number 3 to do that. And again, you could put those numbers in just like we did before, and you will end up with, you know, just really quickly, 6K, and we have 4 to the X and 2 to the Y. All that is entry number, all that is entry number 1 and entry number 3 on the bottom, which would be 3K. We got 2 to the X and 2 to the Y. Again here, the 6 and the 3 will give us a 2. The K's will cancel. The Y's over here will cancel. When we do that, we'll get 2 to the X, and we see X is equal to 1 as well in my particular example. And that would be the order with respect to X in this particular case as well. So you could use this sort of mathematical approach to figure out, you know, the orders of each of those. And as we'll talk about next time, once you figure that out, you will have the completed rate law, and you could go back and actually figure out the value of the rate constant in that particular case. But the idea here is to pick 2 entries from the table where you keep one of the concentrations constant and vary the other, and then go back and do the opposite, keep the other one constant and vary the one that you held constant the first time. Any questions on that there? And again, we'll pick up more of this on Tuesday. Yeah. All right. So we'll take a little break. 11:30 is lab. We're going to do some molarity type exercise.